Welcome to Physics with Dr. P. I'm going to be going through the May 2017 A-Level Paper 1 for Edexcel Physics. So without any further ado, let's get straight into it. So, Section A. Which of the following is not a vector quantity? Remember, a vector is something that has both a direction and a magnitude. So let's think of which one of these does not make sense as having a direction. Acceleration definitely has a direction, momentum definitely has a direction, and velocity definitely has a direction, so it must be distance. Question 2. Which of the following can be used to determine the magnitude of velocity? Let's see, the area under an acceleration time graph. That sounds about right. Let's just double check the rest. The area under a velocity time graph, now that is the displacement. The gradient of an acceleration time graph is not something that we ever are interested in, and the gradient of a velocity time graph is the acceleration. So it must indeed be A. Okay, question 3. Let's see. A small plastic bead is released below the surface of water and rises towards the surface. The diagrams show the forces acting on the bead as it rises with constant velocity. Now, the fact that it rises with constant velocity means the forces must be balanced. That means we can immediately discard B, because we can see that in B the downward forces, if we add them together, are going to be bigger than the upward forces. And same thing I would say with D. So that leaves A and C. Which diagram correctly represents the directions and relative magnitudes of the forces? Now, the upthrust is always going to be up, and as it is in both of these cases, the weight is always going to be down, as it is in both cases, so the difference is in the direction of the drag. Now, drag will always act to oppose motion, and if it is rising, motion is going to be upwards, so drag is going to be downwards, so it must be C. Question 4 is at the bottom of this page. A hairdryer is used for 3 minutes. The operating current is 6 amps. So let's write current is 6 amps, time is 3 minutes, which is 180 seconds. The charge that flows is going to be given by current times time, because current is defined as charge passing per time. So if we multiply these together, 6 times 180, the answer is going to be 1080 coulombs. Okay, question 5. A student is deriving an equation for the total resistance of resistors in series. She writes the following steps but does not justify them. Now, I'm going to use this nice big space that we're given to draw a diagram, because as I always say, all the physics is in the diagram. Everything that follows is going to be maths. So, we have a voltage source, V, and we have two resistors. Let's call them R1 and R2. And we are going to say that the voltage in R1 is V1, the voltage across R2 is V2, and we're going to need to write some currents. Now, the current through R1 we're going to call I1, the current through R2 we're going to call I2, and the current through the cell we're going to call I. So now we have all of the symbols that are going to be used. Let's see. We want to find which step is justified using conservation of charge. So all the steps are correct. V equals V1 plus V2. Now that is a statement of Kirchhoff's voltage law, so KVL for Kirchhoff's voltage law. That's actually conservation of energy, not of charge. So it's not that one. But V equals IR. That's Ohm's law. So that is, again, not conservation of charge. Step 3, so IR equals I1R1 plus I2R2. Now, if you notice, that's just a combination of step 1 and step 2. This is restating that V, which is IR, is equal to V1, which is I1I1, plus V2, which is I2R2. So it's not step 3. That leaves only step 4. Well, let's double check. I equals I1 equals I2. Now that is Kirchhoff's current law, which is indeed the conservation of charge. But why is it the conservation of charge? Well, it's telling us that the charge carriers that flow through the cell are the same as the charge carriers that flow through R1 and through R2. In other words, none disappear or appear in going from the cell to the resistors. So the charge is conserved. The flow of charge is going to be the same everywhere in a series circuit. Question 6. A ball is kicked, giving it an initial velocity v at an angle of 35 degrees to the vertical. Once again, I'm going to draw a diagram. Now let's be very careful, because normally in projectile motion questions the angle is given from the ground. Instead here it's being given from the vertical. So we have 35 degrees to the vertical, and the ball remains in the air for a time t. So the ball is going to make some kind of trajectory like this, hit the ground again, take a time t, and because in projectile motion we assume that there is no horizontal acceleration, so let's write that down as well. That implies that the distance x that it's going to travel is just equal to the horizontal component of the initial velocity multiplied by time. So all we need to do is work out what this horizontal component of the velocity is. Well, it's going to be this side of this triangle, VH, and that's the opposite 35 degrees, so it is going to involve sine, right? So katoa, so sine opposite, we have the hypotenuse, it's V, so we can write down that sine 35 equals opposite VH divided by hypotenuse V, which tells us that VH equals V sine 35. So putting that all together, we're going to get that x, the distance travelled over the ground, is VHT, which is V sine 35 times t, and that looks like answer C. Let's just double check. It's not A because that's a cosine, it's not B because time should not be in the denominator, and it's not D for the same reason. So it can only possibly be C. Let's move on to question 7. A series circuit consists of two resistors with resistances R1 and R2 and a battery of potential difference V. Once again, I like to be able to visualize it. So quick sketch. Here we are, R1, R2. Which of the following gives the potential difference across the resistor with resistance R2? Now, two resistors in series, this is also known as the potential divider. That means that the potential supplied by the cell is going to be divided between the resistors accordingly to the ratio of their resistances. But let's do this properly. So let's first of all, similarly to the previous question we saw with Kirchhoff's law and Ohm's law, that's what we're going to be using. So we know that if we want the potential difference in R2, we want to find V2. Now V2 is given by the current through R2 times its resistance, and by Kirchhoff's current law, the current is going to be just the same everywhere in a series circuit, so we need to find this total current. Now the total current is going to be given by the potential difference that we supply divided by the total resistance. So let's write down over here that I is equal to V divided by R1 plus R2, and putting this all together we're going to have V over R1 plus R2 multiplied by R2 to give us V2. Now let's look carefully. That looks like answer D. It's not C because that's got R1 in the at the top, which we don't want, and it's not either of A or B because they do not have the denominator we want, which is R1 plus R2. Question 8. A light-dependent resistor and a negative temperature coefficient thermistor are connected in series. Which of the following combinations of illumination and temperature will result in the highest combined resistance? Now, if they're connected in series, that means their resistances are going to add. So to get the highest combined resistance, we need to maximize the resistance of each one in turn. Now for the LDR, resistance increases as light intensity decreases. So we're definitely going to need darkness. So it's not going to be either C or D. And then for the negative temperature coefficient thermistor, now negative temperature coefficient means as the temperature increases, the resistance decreases. In other words, there is a negative correlation between temperature and resistance. So to increase the resistance, we must lower the temperature, so it's going to need to be dark and cold. The answer is A. Okay, that's the end of the multiple choice questions. Let's get into some real physics now. Question 9. A torch uses a 1.5 volt dry cell. Over time, the light intensity produced by the torch decreases as the cell goes flat. Student A sets up the following circuit in an attempt to measure the EMF of a cell. Explain why the voltmeter reading will not be the EMF of the cell. Well, that is because we're measuring the voltage across the bulb. We're not taking into account anything else that might be causing a drop in voltage from the EMF, and really we're going to have an internal resistance. The cell is going to be a pure source of voltage, which we call the EMF, in series with an internal resistance. So we will say something like, for 2 marks, first of all, cell has internal resistance, and it's crucial that you mention the phrase internal resistance. For the second mark, well, what are the consequences of that? The consequences are that some voltage is dropped by this internal resistance. In other words, the cell is supplying some energy per unit charge, that's the definition of voltage, but some of that energy is dissipated by the internal resistance, so not all of it goes to the light bulb. So this voltmeter is not going to measure all of it. It is going to measure a voltage which is lower than the EMF. But this is all you need to say for the 2 marks. Let's go on to part B. Okay, this looks a little bit more substantial. 5 marks. Student B correctly determined the EMF of an unused cell as 1.63 volts and its internal resistance as 1.15 ohms. So let's draw that again. You may see a running theme here. So we have 1.63 volts in series with 1.15 ohms. And that is connected to, well, let's assume it's a light bulb again. Doesn't really matter too much. He repeated this after the cell had been used for several weeks. When a voltmeter was connected directly across the used cell, the reading was 1.36 volts. A bulb of resistance 5.92 ohms was then connected across the used cell, and the reading fell to 0.84 volts. Student A suggests that the cell goes flat as it's used because the EMF decreases. Student B suggests it's because the internal resistance increases. So determine whether either student is correct. So we're going to need to find the EMF, and we're going to need to find the internal resistance. 2 marks for each of those, and then the 5th mark is going to be for some kind of concluding statement. Let's see. When a voltmeter is connected directly across the used cell, so what we have is this. We have the EMF, and we have the internal resistance connected directly to a voltmeter. Now, an ideal voltmeter has infinite resistance. That means that no current will flow. So the voltage that this is going to measure, V, is going to be the EMF minus current times internal resistance, but as we have an infinite resistance, the current is going to be 0. So in this case, this is essentially an open circuit, right? We'd normally connect a voltmeter in a closed circuit where there's other things going on. Here we have none of that. We are testing the open circuit voltage, which is the same as the EMF, because no current is flowing, so there can be no dissipation in the internal resistance. That tells us that the EMF is 1.36 volts. So 2 marks for determining that. Then let's draw what's going on. Now that we know what the EMF is, we can put that in. We have 1.36 volts, we have some internal resistance R, and that is connected to a light bulb of 5.92 ohms. And when connected across the the bulb was then connected across the U cell, and the reading fell to 0.84 voltmeters. So the voltmeter, 0.84 volts. The voltmeter is still connected across the cell like this, and it measures 0.84 volts. Well, if we have a voltmeter connected like this, it's measuring the voltage across the cell, but it is also measuring the voltage across the light bulb, right? You can think of these 2 points as being on either end of the light bulb. So we know that the voltage in the light bulb equals 0.84 volts. That means the current in the light bulb will equal 0.84 volts divided by 5.92 ohms, which is, let's see, it is 0.142 amps. And now I'm going to make use of this formula for the voltage in terms of the EMF and the internal resistance. I think I'm going to need to make use of some of the space under the question. So we know that 0.84 volts, the total voltage across the cell, is equal to the EMF, which is 1.36, minus current times internal resistance. And if we rearrange that, we're going to get that 0.142 times internal resistance is 1.36 minus 0.84, which is 0.52 volts. So the internal resistance is 0.52 divided by 0.142, which is 3.66 ohms. So that's another 2 marks for working that out. Let's try and get the 5th mark. Let's remember what we're trying to actually answer. Student A suggests that the cell goes flat as it's used because the EMF decreases. Well, we can see that that's the case because the EMF originally was 1.63. So A is correct. And student B suggests it's because the internal resistance increases. Well, if the internal resistance was 1.15 before and now it's gone up to 3.66, that is also true. B is also correct. And that's it, we're done. 2 marks for calculating the EMF, 2 marks for calculating the internal resistance, and 1 mark for some concluding statement. Let's move on. Question 10. The photographs show 2 types of caliper being used in turn to measure the diameter of an iron rod. So the first one gives a reading of 12.17, the second one gives a reading of 12.2. State the resolution of each of the calipers and compare their use for measuring the diameter of the rod. So caliper 1 had a resolution of it was taking measurements to the nearest 0.01 millimeter, and caliper 2 had a resolution of 0.1 millimeter. So That's 2 marks because we have stated the resolution of each of the calipers. We've done the first thing the question asks. And then compare their use for measuring the diameter of the rod. Now, we just need to make 2 valid points. So first of all, we can see that there's a higher resolution for caliper 1, which is going to lead to a lower uncertainty, because to work out the uncertainty, we need to find the resolution as a fraction of the actual measurement. Now, the measurement is pretty much the same in both cases. It's the same iron rod we're measuring, so the uncertainty will depend on the resolution. So caliper 1 has lower uncertainty. That's certainly something we can say for a mark. Something else, well, let's see. Caliper 2, now this involves making a judgment. I don't know if you've used one of these vernier calipers, but we need to see where these small marks line up. And if we're making a measurement of 12.2, now we can see that the 12 comes in because we're at 1.12, so that's the 12, but then the 0.2 is because this second tick lines up. But that involves a judgment. It might well have been read as 12.1 or 12.3. So caliper 2 involves human judgment, while caliper 1 gives a direct reading. So, but caliper 1 gives a direct reading. That's another thing that we can say. Finally, we can say that, well, caliper 1, yes, it has a very, very fine resolution, but maybe it's so fine as to be overkill. Maybe we don't need something that is that sensitive. We could say something like the diameter of this iron bar that we're measuring might vary more than this resolution. So another valid point, diameter of bar may have variation larger than resolution of caliper 1. Then resolution 1. So these are all things that you can say, and that's more than enough to get the 4 marks. Let's look at part 2. The value obtained from caliper 2 was used to determine the cross-sectional area of the rod, and the electrical properties of the rod were investigated. Calculate the drift velocity. So if we're going to be finding drift velocity, let's just write down the drift velocity formula straight away. The current is equal to the charge carrier density times the cross-sectional area times the drift velocity times the charge per carrier. Let's see which of these we know. We know that the current is 1.9. We know the charge carrier density, that's N, 1.7 times 10 to the 29. The area we don't know, but we know the diameter. So let's work out the area. So that means that the area is going to be pi r squared, where r is half the diameter, so pi d over 2 squared. But of course, we're going to need this in meters. So it's going to be pi times 12.2 millimeters is 0.0122 meters divided by 2 squared. And I haven't actually worked out that number, I just put it all straight in my calculator, but we'll get there in a second. This is what you would put in. So n times a, which we have, is pi times 0.0122 over 2 squared, times drift velocity we need to find, and times charge. Well, they're electrons. All electrons have exactly the same charge, which is 1.6 times 10 to the minus 19. If we make v the subject, we just divide through by all of these other things, and you should find that v is about 5.98 times 10 to the minus 7 meters per second. You must quote the units, right? That's a lost mark. If you don't, the unit is not given in the answer, but it is a velocity, so it is in meters per second. So 5.98 times 10 to the minus 7. The mark scheme, I believe, gives a tolerance of anything between 5.9 and 6.0. So I would encourage you to have a look at the mark scheme as well, which is freely available. Let's move on. Question 11. A motorist received a speeding penalty notice from the police for a short journey along 120 meters of road. The car specification states the minimum time for the car to accelerate from 0 to 60 miles per hour is 9.5 seconds. Show that the maximum value for the average acceleration of the car over 9.5 seconds is about 3 meters per second squared, and 1 mile is 1,600 meters. So first of all, we're going to need to convert 60 miles per hour to meters per second. So 60 miles per hour, well, that's 60 times 1,600 meters, 60 lots of 1,600 meters, because each set of 1,600 meters is a mile, divided by 1 hour. Well, an hour is 60 times 60, it's 3,600 seconds. And if you work that through, that comes out to be about 26.7 meters per second. Now, what else have we got? We're trying to find the acceleration. This looks a bit like motion in a line with constant acceleration because we're just looking at the average acceleration. So, this is a SUVAT problem. Let's think which of these we have, which of these we don't have, which of these we don't care about. S is 120 meters, that's the distance traveled, or rather the displacement. And we're accelerating from 0, so U is 0 meters per second, the initial velocity, while the final velocity is 26.7. The acceleration is what we're trying to find, and the time is not mentioned, so we don't care about that. So I'm just going to leave it blank. We want something involving S, U, V, and A. Well, which one of... Ooh, no, I'm wrong. We are given the time. It is 9.5 seconds. So actually, we've got more than enough information. We've got the car specification states the minimum time for the car to accelerate from 0 to 60 is 9.5 seconds. Show the maximum value for the average acceleration of the car over 9.5 seconds is about 3 meters per second. So we're not going to be using this. So that is, maybe it's good that I made that mistake, because this is a mistake that you would very easily make because this 120 meters is given right at the beginning. But actually in part A, it doesn't mention the road at all. Right? This is purely theoretical. We're given an initial speed, a final speed, and a time. And we need to find the acceleration, which is given by change in velocity divided by time. So it's 26.7 divided by 9.5. And if you put that through a calculator, you will find 2.8 meters per second squared, which is indeed approximately equal to 3 meters per second squared. So 2 marks, 1 mark for selecting the appropriate formula, 1 mark for getting the right answer. Now, the police recorded a maximum speed for the car of 20 meters per second. The motorist knows that the speed at the start and end of the 120 meter journey was 0. Assume that the car had constant positive acceleration equal to the value in part A for the first 60 meters of the journey, and constant negative acceleration of the same magnitude for the final 60 meters of the journey. So we've got 2 values of acceleration, so we should do 2 SUVAT problems. We'll split the page in half and say that we've got S, U, V, A, T speeding up, and slowing down. S, U, V, A, T. Now let's see what would happen if we had an acceleration of 3 meters per second squared, as we've just found. And we started at 0, and we did that over half of the journey, so over 60 meters. What is our maximum speed going to be? So we are trying to relate S, U, V, and A. This time we definitely don't care about the time, and we're going to be using V squared equals U squared plus 2AS. But U is 0 in this case, so we're going to have that V squared equals 2 times 3 times 60. And if we take the square root of that, we're going to find that V is going to be approximately 18 meters per second. So that means the police recorded a maximum speed of 20 meters per second, but given these parameters, that couldn't possibly have been the case, because if we start from 0 and we accelerate at the maximum possible acceleration that the car has, we're not going to get up that fast. So yes, the motorist should challenge the penalty notice. So what would you actually write? You would say, should challenge because accelerating at 3 meters per second squared could not reach 20 meters per second over that distance. Or alternatively, you could say to reach 20 meters per second would need an acceleration greater than car's maximum value, the car's maximum acceleration. So either of those points would be more than enough to get those marks. Let's keep moving. Part C. Explain why the assumption about the acceleration may not be correct in practice. So remember, we assumed that we have a constant acceleration for half of the journey and a constant acceleration of the same magnitude for the other half of the journey. In other words, the velocity time graph will look like this, with an equal gradient going up and coming down. Well, why may that not be correct in practice? There's lots that we can say, but first of all, it is unlikely that we will actually have a truly constant acceleration. And why is that? Because we have air resistance. So air resistance increases as the velocity increases. And what that's going to mean is the faster you go, the higher resistive force you have, which is going to decrease your acceleration. So actually it's more likely to do something like this. It's going to curve. It's not going to be a straight line on a velocity time graph. Anything else? So that's the assumption that the acceleration is constant. What about the assumption that the deceleration is the same as the acceleration? Well, probably the braking force is going to be higher than the driving force. So there is, let's say, no guarantee that braking force equals driving force. In fact, most likely the braking force is going to be larger than the driving force because we need to be able to stop over as small a distance as possible for safety. So in fact, braking force is probably higher than driving force. So there we go, 2 points challenging the two main assumptions of the previous parts of the question. Let's keep moving. Question 12. A student investigates how the efficiency of an electric motor being used to raise a load varies with the weight of the load. The time taken for the motor to lift the load from the floor to the maximum height was measured using a stopwatch. The load was varied by adding weights, each marked 1 Newton. The spreadsheet shows the student's results, columns A to E, and calculation, column F. Explain how the value in cell F4 has been determined using the results obtained. So we're looking at this 0.17. Well, we want to find the efficiency, and the efficiency is given by energy out, or the useful energy out, divided by total energy in. So this is what we're trying to use, and we're going to try and determine the useful energy out and the total energy in. So if we've got a change in height, the useful energy out is going to be a change in gravitational potential energy, particularly if we start it stationary and after we've raised it to a certain height we stop it. So it's not moving anymore, we're not going to have any kinetic energy, so really it's only the gravitational potential energy. The energy in is given by power times time, because what is supplying energy to this motor? It's the electric current. We know how to find the power using current and potential difference. So GPE divided by power times time. Let's see if that is going to give us a value of 0.17. Now the gravitational potential energy is mgh. In fact, we don't even need to find mg because the load is in newtons. It is the work done against gravity, so it's the weight multiplied by the height. So it's going to be 4 newtons times a distance of 0.825 meters. That's going to be divided by the power, which is current times potential difference, so 2.1 times 4.3. Remember, this is determined using power is current times voltage, multiplied by the time taken, which is 2.19 seconds. And if you put all of those through a calculator, you will indeed find an efficiency of about 0.17. Units of efficiency, it doesn't have any, because we're dividing an energy by another energy. If you put a unit on the end of this, you will lose a mark. So it is just the number 0.17. Okay, next page. Really, that's all you need to do for 12 part A. 12 part B. The student uses the spreadsheet to plot a graph. The student concludes that the efficiency of the motor increases with the weight of the load up to a maximum when the load is 6. Criticize the investigation and the conclusion. Now, 5 marks, it's probably more than 5 points that you can make here, but immediately I can see the student has talked about what happens going up to a maximum, but you haven't talked about what happens as the load increases further. So this is an incomplete conclusion. Does not say what happens when load is greater than 6 newtons. Anything else? Each measurement has only been done once. Each value of load has only been investigated once. So some of this variability, some of this zigzagginess might go away if we repeated readings and took an average. So should have repeated readings. And taken an average. Anything else? Oh, we have an anomaly at 5 newtons that we haven't said anything about. no discussion of anomaly. And what else? Well, we had lots of things varying. So if you look at the table of results, we're changing the load. We've got a variable current, we've got a variable potential difference. The time is variable. The only thing that we're controlling is the change in height. So I would say that some more control variables would have been good. And finally, we've got a maximum when the load is 6 newtons. Well, around that maximum, we could have tried to find exactly where it is by taking finer divisions of weight around that. So finer intervals of load, especially around 6 newtons. So we may have wanted to look at 5.5 newtons, 6.5 newtons, see if we can pinpoint where exactly that maximum occurs. So all of this, we have 5 points, 5 marks. Any reasonable points would have been accepted, but of course that raises the question of what is reasonable. This is a guideline, and for questions like this, I would very much encourage you to look at mark schemes. So take it from me as a physics teacher, even physics teachers often look at mark schemes to make sure that everything that we're saying is correct and complete. It's very easy to forget small things, and when you're training yourselves to do exam questions like this, remember you are trying to appease an examiner, so you should try and look at what examiners want year in, year out. Next question. Aha, we have something tilted on a pivot. This looks like moments. A gardener used the trolley to move a paving stone. A force meter was attached to the handle of the trolley. The gardener recorded the following measurements when the trolley was at rest in the position shown in the diagram. Mass of the trolley and paving stone is 18.5 kilograms, length of trolley is 97, force on handle is 50 newtons. Determine the distance of the center of gravity of the loaded trolley from the wheels. So, the center of gravity, let's just draw it in a position like here. Let's call that distance L. And we're going to have a weight of 18.5 times G acting down, and we've got a weight of 50 newtons acting up, and the length of trolley is 0.97 meters, 97 centimeters. Now this is at an angle, and if you notice we have an angle between the forces and the lengths, so we are definitely going to need to put an angle in here. So let's call that theta. And now let's look. Determine the distance of the center of gravity of the loaded trolley from the wheels. Let's just write down our principle of moments. So I'm going to resolve about the wheel. I'm going to call clockwise my positive direction, so I like to write it like this. Fix my pivot and state which direction I'm taking as positive. And then we are going to have, well, let's see. If we have an angle theta, then we want the perpendicular distance from the force to the pivot. That would be this distance here. And if this is the angle theta, that is going to be given by the cosine. So the distance from the pivot to that force is L cosine theta multiplied by 18.5 G, and that is acting clockwise, so that is definitely positive. And then anti-clockwise, so gaining a minus sign, in exactly the same way, the length is 0.97, so it's going to be 0.97 cos theta. So 0.97 cos theta multiplied by 50. And that's it. There are no other forces acting at a distance from the pivot. We're going to have a reaction force from the ground at the pivot. However, that's going to be at a distance of 0 from the pivot, so its moment will be 0. So this is all. Now notice, we don't know what the angle is. It turns out it doesn't matter, because this factor of cos theta will cancel out. Nevertheless, the mark scheme is explicit that if this is not seen, if cos theta is not in your working, you will not get the full marks. So you do need to be thorough with it, even if in this case it ends up being inconsequential. So let's rearrange it. We're going to have L times 18.5 G equals 0.97 times 50, and if we rearrange that, G is 9.8 meters per second squared, so L will end up being 0.27 meters. So L is 0.27 meters. And again, remember, you need this cosine theta to get the full marks, even if it ends up cancelling out. Next part. The gardener pulled the trolley and measured the applied force while the trolley was moving. The direction of the applied force is 25 degrees to the vertical, as shown by the arrow. So let's just add the angle on explicitly, 25 degrees. Calculate the magnitude of the applied force. Assume that the vertical component of the force remains 50 newtons. So let's just draw a little vector diagram. We have 50 newtons here, and we have some vertical component, some horizontal rather component. Let's call it FH. So what's the magnitude of the applied force going to be? Well, first of all, let's work out what FH is going to be. This magnitude is going to be F. So, in fact, do we even need to? I don't believe we need to, because we have an angle, we have a hypotenuse, F, and we have an adjacent. So let's just write down the formula for cosine. Cosine 25 equals adjacent divided by hypotenuse, F, which means that F is going to be 50 divided by cosine 25, which is 55 newtons. Okay, that's all there is to that one. It's just, if you draw the vector triangle, it becomes a lot easier to figure out. Then, the gardener continues to walk and pulls the trolley a distance of 15 meters in a time of 4.2 seconds. Calculate the power developed while pulling the trolley. Now, power is given by work done divided by unit time, and the work done is the force times the distance travelled in the direction of the force. Now, the distance is in a horizontal sense, so in the direction of the force means we're only interested in the horizontal force. So let's be explicit. We're dealing with FH. Everything else we know. The distance is 15 meters. The time is 4.2 seconds. And if we just go back to the diagram, what we're interested in is finding this FH. Now, we could use F to find it, but I think it's easier to just use information given to us directly. So we're trying to relate the adjacent, the opposite, to an angle. So that's going to be tan. So we've got tan 25 equals opposite over adjacent equals FH over 50. That's what we're going to use. So rearranging that, let's just write that down here. FH will equal 50 times tan 25, which comes out to be 23 newtons. So to find the power, we're going to use 23 newtons times 15 meters over 4.2 seconds, and that answer ends up being 83 unit. Well, it's a power, so it must be watts. So power is 83 watts. Okay, question 14. The graph shows how the current through a filament bulb varies with the potential difference across the bulb. Determine the resistance of the filament bulb when the potential difference is 7 volts. So when we have a potential difference of 7 volts, the current is 1.44, and the resistance is not the gradient of an IV graph. That's a common misconception. It is literally the voltage divided by the current. So resistance is V divided by I. So it is 7 volts divided by 1.44 amps, which gives about 4.9 ohms. That's it. So common misconception is that you need to find the gradient. You do not. All you need to do is just do voltage divided by current. So 4.9 ohms. Next question. Sketch a graph of resistance against potential difference for the filament bulb over the range 0 volts to 7 volts. So we start off with a constant value of resistance, which we can see by this gradient. So when the potential difference is 0, we definitely do have a value of resistance. Now we can see that as the potential difference increases, the current is not as high as it would have been had it continued in a straight line. So the resistance must be increasing. So that is enough to get the 3 marks. Just a graph that looks like that. We cross at a non-zero value and it rises up. Then this little star, by the way, here means that this question is going to be marked for quality of written communication. So explain the variation of resistance with potential difference for the filament bulb in terms of particle behavior. Now here is one where, again, reading the mark scheme is going to give you a lot of guidance in how you should be answering this kind of question. But the argument goes more or less as follows. As the voltage across the wire increases, well, what's voltage? That's energy per unit charge. So we're pumping more energy in. Electrons have more energy. Or they have a higher velocity, higher drift velocity. Now what that means is that we have more frequent collisions with the lattice of ions. And in these collisions, more energy is transferred. And what that does, if you're transferring lots of energy, we will have an increase in temperature. You're going to have the lattice vibrating more, heating up. So temperature increases, which means that the lattice of ions vibrates. And that means that you're going to have a higher rate of collisions. If you're vibrating, you're a bigger target, right? You're moving around, so that means higher. Let me not write like a GCSE students, more collisions. Let's write greater rate of collisions. And what that ultimately means is that voltage is not proportional to current. Current increases less than if it were proportional to the voltage. So again, in these wordy questions, there is a style that they like to see, and the best way to work out and internalize this style is to read lots of mark schemes. All right, hopefully that was useful. And onwards to part B, perhaps in another video.